We're going to build a neural network. In this episode, episode 3, we're going to do the handwritten example where we calculate the output of the network, we compare it to the correct answers of the network, and then we will backpropagate and update all the weights so that we can get the correct answer in the future. So these are all the weights that we'll be updating. And then we'll actually feed input data through the network through this first input layer. Then we'll calculate the outputs of H1 and H2. Then we'll calculate the outputs of the network, Y1 and Y2. The output of each of the nodes is followed by the formula N1 W1 plus N2 W2 plus B1. That is each, for this specific node right here, that is each of its inputs, N1 and N2, times each of their weights respectively, which is W1 and W2. Then it'll be plus a bias, and that will get you the output of the node. Then, the output of the node is wrapped in this activation function, sigmoid. We'll denote the difference between the output of the network, which is out of H1 or out of H2 or wherever the nodes, versus the activation of the actual node, which is the output of the node wrapped in the squisher function. The outputs will be put on a scale between 0 and 1. That'll make a difference later on when we're doing the backpropagation. With this given example, and mind you, all the example inputs and the bias and the weights are all arbitrary. I just picked them for this specific example. I tried to color code them right here. It might be a little bit easier to map them. For this first example, we have two inputs, which are x1 and x2, and their values are 0.05 and 0.1. So you could see this is x1, that's m1. That's why they're both blue. Blue, blue, that one's blue. So in short, the input is mapping from this node. Anyways, x2 is n2, which is why the lines for that one are purple. Other than that, the colors have no value. Anyways, we also have the initial weights. You'll notice W1, W3 are blue, W2, W4 are purple, and W1, W3 are blue, and W2 and W4 are purple. Okay, so now we're going to calculate the outputs of H1 and H2, because M1 and N2 are already given. Okay, so to calculate the output of H1, you can see that it will be M1 times W1 plus N2 times W2 plus B1, which is why we have output of H1 is equal to M1 W1 plus N2 W2 plus B1. That gets you 0.377. Then the activation of H1 is the output of H1 wrapped inside the sigmoid function, which gets you the value of 0.5933. And in the same way, we have the activation of H2, which is 0.59688. You can see that the activation of H2 will come from M1 times W3 plus N2 times W4 plus B1. That'll get you the output of H2. Then you wrap that output inside the activation function, sigmoid, and that will get you that value right here, which is 0.59688. So that is how we calculated the outputs that will be coming out of H1 and H2, which are these two activation values. Now, let's calculate the outputs of Y1 and Y2. And you can see it will be the activation of H1 times W5 and the activation of H2 times W6 for Y1. And if you look, the output of Y1 is equal to the activation of H1 times W5 plus the activation of H2 times W6 plus B2, as you can see. And we get the value of 1.1059. In the same way, then the activation of Y1 will be equal to 1 over the sigmoid function, taking in as the output of Y1 as its input, and then you get 0.7514. So that is the actual output of the entire network, which we call the activation. So the output of the Y1 node, which is the activation, is 0.7514. In the same way, we'll get the activation of Y2, which is equal to 0.7729. That's the activation of Y2, which you could see we get from the activation of H1 times W7, the activation plus the activation of H2 times W8, plus the bias 2. And that gets you the output of Y2, which you wrap inside the sigmoid function gets you the activation of Y2, which is 0.7729. Now that is all it is for the actual feed portion of the network. So that is how we get the two output values of the network, which is 0.75 and the 0.7729. Now let's see how well the actual network did with the correct target values that we were looking for. Well, you could see the target values that we were looking for T1, which maps to Y1, was 0.01. So as you can see, right here, T1 was looking for 0.01. Well, you can see the activation of Y1 is 0.75. So you could see that it actually did pretty badly. And the target value for T2 was equal to 0.99. You can see that the activation value we got for Y2 was 0.77. So it did pretty bad, but not as bad as the activation of 1. So now that we've calculated what the output of the network is, and compared it and saw that it actually did pretty poorly, now we're going to go ahead and do the backpropagation so that we can actually correct the network. Now, before we do the backpropagation to correct the network, I want to take a look at how this network works so that we'll be able to see how the backpropagation is going to actually work. To correct this network, the only thing that we can adjust are all the weights and also the bias as well. So here's all the weights and here's the bias. These are the only things that can be adjusted. I kind of covered that in the last video. So if we want to fix the weight of 5, we would first have to find the contribution 5 has to the actual error of the network. And to find the error it has to the network, we have to trace our way back. So you can see it starts with weight 5, which goes into the Y1 output, and then the activation of the Y output is what the actual value we received is, which is compared to the target value to receive the cost. So if we're working our way backwards, we can look at this diagram here. It starts with the cost, which comes from approximately T1 minus the activation of Y1, which makes sense because T1 maps to Y1. That's the cost, and it comes from T1 in the activation of Y1, and it traces back to the output of Y1, which we calculated or we put it inside the activation function, and then the output of Y1 comes from that formula. The output of Y1 comes from the activation of H1 times W5, the activation of H2 times W6, plus the bias. So that's why we have as inputs to this output of Y1, weight 5 times activation of 1 plus the bias. Technically, there's also, I believe, it'll also be weight 6 in H2, but considering that we're only looking for the contribution W5 has to the error, you'll see why that won't make a difference, at least in terms of this diagram, and we'll be able to use this diagram to calculate all the contributions that all the weights have to the error, and then make those corrections. To find out how the contribution that first activation of Y1 makes to the error, you would do the partial derivative. This is the math portion of it. Now, I already do the math for you, but if you know how to do the math, then you're fine. But anyways, the partial derivative of the cost with respect to the activation of Y1 is equal to negative, in parentheses, T1 minus activation of Y1. And that will get you this value. Now, we have to work our way back there. The partial derivative of the activation of y1 with respect to the output of y1 is equal to the sigmoid. All we're doing with these steps are seeing the contribution each one of these pieces have to the error all the way back to the weight 5. Like I said, we're at this output of y1 step, and the contribution that the output of y1 has with respect to the activation of y1 is sigmoid prime of the output of y1. Then we have, now we're trying to find the specific contribution, weight 5 has to the error. So you could see the specific the formula for output of y1 is equal to weight 5 times the activation of h1 plus weight 6 times the activation of h2 plus b2. The partial derivative with respect to this is the activation of h1. And that's the reason why I said you don't have to worry about h2 and weight 6 in this specific instance, because by partial derivative, it will turn all those into 0 values. The activation of h1 is the partial derivative of weight 5 with respect to the output of y1. With that, we have the total contribution of weight 5 with respect to the total error is equal to the contribution of the activation of y1 with respect to the output of the cost times the contribution of the output of y1 with respect to the output of the activation of y1 times the contribution of weight 5 with respect to the output of y1. Now that is the whole diagram that we just went through, but we'll actually be going through all those calculations. This was just more of a visual thing so you could see how it looks. Okay, so starting with trying to get the error contribution of weight 5, we'll go ahead and calculate it. First, we calculate the total error, and the total error is equal to the sum of all the targets minus the activation squared times 1/2. So first, we have target 1 minus the activation of y1, which is 0.01 minus 0.75 squared, plus 1/2 times, in parentheses, 0.99 minus 0.77 squared. And that's so this is the error for error 2, and this is the total error for error 1. If you sum them together, you get 0.298. And then you see that's the error for the first one, and that's the error for the second one. So we're going to actually calculate the contribution of weight 5 to the total error. So like I said beforehand, the contribution of weight 5 to the total error is equal to the contribution of the activation of y1 to the output of the total error times the contribution of the output of y1 to the activation of y1 times the contribution of weight 5 to the output of y1. And you can see here we go for the first one, which is the contribution of the activation of y1 to the error total, and we do this calculation, and then we get 0.743. That's this first piece. Now the next piece we have to calculate is the contribution of the output of y1 with respect to the activation of y1, and that this is the actual sigmoid function prime, and then we get 0.1868. Then the last piece is we have to calculate the contribution of weight 5 with respect to the output of y1. And then we get that, looking at the formula, this is the actual weight 5. The partial derivative of this gives you the activation of h1, which is 0.59. Now that we have these three pieces, 1, 2, and 3, in this next piece, we multiply those three values together, and then we get the total change for weight 5 is equal to 0.08216. Now this is the percentage that weight 5 is contributed to the error. which leads into how we actually update the actual weights. So this right here we have is a learning rate. Now this can be adjusted anywhere between any number that you want. This is the step that you want to take in the direction. The best way to think of it is this contribution of weight 5 to the total error is a ratio. So you have to choose how much you want to completely adjust the previous value of weight 5 towards the correct solution. And this is something that you keep making adjustments to more and more, and over multiple simulations it'll get closer and closer to the correct output. Ultimately, we take the previous value of weight 5, which was 0.4, minus 0.5 times that change in weight 5, and we get the new weight for weight 5 is equal to 0.3589. Now in that same way, you could calculate the error. You could calculate and then update the new weights of weight 5, weight 6, weight 7, weight 8. And if we look at the diagram, you could see that all these weights are in the same layer. So all of them will be calculated in the same way. In the same way that we calculate the weight, we calculate the error of weight 5, which came from the error, if we're going from this way, because this is how it will work, it would be the error of weight 5 with respect to the output of y1. Then it was the contribution of the output of y1 to the activation of y1, which is the squisher function, and then the contribution of the activation of y1 to the error total. This is when we compared it to the correct value. And that is how you could do that same process to find the contribution all these weights did in this layer to the total error. That's how you do it for all the weights. And if you want to do it for the bias, if you're good with math, you could see that, where is it? To calculate the contribution the bias made to the error, all you'd have to do is take the partial with respect to the bias as opposed to the weight 5, and it would just give you a value of 1 because the bias is a constant. Anyways, now that we've calculated, now that we've calculated all the weight adjustments for the output layer, now we'll do weight 1, weight 2, weight 3, and weight 4. These are the weights in this layer, and they'll all be done in the same way. And this is the tricky one, so I'd recommend taking a little bit of time to really look at this one. Okay. The contribution that weight 1 has to the total error is equal to the contribution that the activation of H1 has to the total error times the contribution of the output of H1 to the activation of H1 times the contribution of weight 1 to the output of H1. If we look at it right here, to find W1's contribution to the whole error, we first have to find its contribution to H1. Now H1 has a contribution to this guy's output as well as this guy's output. So first we have to find this guy's total contribution. We have to find its contribution to H1, and then H1's contribution to Y1, and then H1's contribution to Y2, and all their activations on the way. So let's go ahead and get started. So we'll start with the contribution of the activation of H1 to the error total, which is equal to the contribution of the activation of H1 to the error 1 plus the activation of H1 to error 2. That is where I showed you it would be H1 right here to right here. Both of these ones. Now we look at it and we have the contribution of the activation of H1 with respect to the error. This should be the error total, which is equal to the contribution of the output of Y1 to the error 1 times, oopsies, right there. Oh, okay, yep. So we have the contribution of the activation of H1 to the error total, which is equal to the contribution of the activation of H1 with respect to error 1, plus the contribution of activation of H1 with error 2. So right now we're doing the contribution of activation H1 to error 1, which is equal to the output of Y1 with respect to the error 1 times the activation of H1 with respect to Y1. And you can see we get the contribution of the output of Y1 with respect to error 1 is equal to the contribution of the activation of Y1 with respect to the contribution of E1, error 1, times the contribution of the output of Y1 with respect to the activation of Y1. And we get the value of 0.13849. We want to get the contribution of the activation of H1 to the so finally we get the contribution of the activation of H1 with respect to the total error is equal to 0.055399 plus negative 0.019049, which is that value right here that we calculated and this value right here. And you see in this step up here we add those two together, and that gave us this first component. So this is the first piece of the puzzle. Now we have to get this piece to the puzzle, which is the contribution of the output of H1 with respect to the output of activation of H1. And that right there is just the derivative of the sigmoid function, and that gets us this output right here, which is 0.2413. And it comes from the activation of H1, and it's substituted in for there. So now that we have this component, the last component to get is the contribution of weight 1 with respect to the output of H1. And that is right here. If we look at the output of H1, which is equal to weight 1 times M1 plus weight 2 times N2 plus B1, we get the contribution will be the partial derivative of weight 1 with respect to output 1. You could see that it would just be M1. So that's why we have M1 is equal, that contribution is equal to 0.05. Now, if we take all those values, which would be the 0.05, that's this component, then we have the 0.2413, which is that one right there, and then we have this one, which is the big one, the contribution of the activation of H1 to the error total, which was all the way down here, which is 0.03635. Then we multiply all those values together and we get the contribution of the error of weight 1 is equal to 0.000438568. Now this is once again the change that we want to make with respect to weight 1, and we multiply that by our learning rate to see how much of a step we'll take. If we want to update weight 1, we have the learning rate, which is 0.5. We have that number that we just got, which is the contribution of weight 1 to the total error, and that is the original weight 1, which is 0.15. We get the newly updated weight 1, which is equal to 0.1497807. And in that same way, we could get the contribution of the error of weight 2, 3, and 4, and then update those weights. So these are the correct updated weights. If you want to check your value, if you want to do it yourself and check the values, these are the numbers to do it with. And to show you again how it would look for it. So if we want to do weight 2, what we would do is first, we would have to find the contribution of H1 to both Y1 and Y2, which we actually did in the previous step. So really all we would have to do is find weight 2's contribution to H1, which would be N2. So you could see, you could see how a lot of our dirty work was done for us, because this right here is the contribution of H1 to the total error, which will be the same for weight 2. We'll need that for that one. You'll do that same process of getting the contribution of H1 to E1 and then H1 to E2. That's repetitive. Then we need the contribution of H1 to the activation of H1. That will be the same. And then all you have to do is find the contribution of weight 2 to the output of H1. And that's as simple as we'll see that's N2. And that is how you get weight 2. All right. Put all these away. And to do the same thing for N, if you want to get weight 3, then all you'd have to do is find H2's contribution to Y1, H2's contribution to Y2, and then the contribution of the activation, the output with respect to the activation, and then you just find weight 3's contribution to H2, and then weight 4's contribution to H2. Alright, so that is how you go ahead and find the contribution of the error, and I'll go through all of them briefly again so that you have a little recap. So, to recap everything, we had our network diagram. It had 2 nodes in the input layer and all these weights. Then we had 2 nodes in the hidden layer, and if you have as many hidden layers, the process would be the same. And then we have all the weights connecting to the output layer, and then we have 2 nodes in the output layer. What we did was we fed in these 2 inputs and multiplied against all these weights to get. So the first thing we did was we forwarded all those values through the network to compute all the outputs of all the nodes. Then we calculated the actual node, the complete output, which was 0.75 and 0.77. These were our network's original guesses. Then we compared those guesses to our target values, which were 0.01 and 0.99. And we calculated the total error, which was the comparison between what our target values and the values that we achieved by the network. Then, after we got those errors, we found the contribution of the weight 5 with respect to the total error. And as you could see, weight 5 goes to the output of Y1, then the output of Y1 with respect to its activation, and then its activation with respect to the total, which lines up with the diagram. Weight 5 to the output of Y1, Y1 to its activation, activation to the total error. And then we went ahead after we calculated each of those parts. You can see right there, once we got all those parts, weight 5 right here. After we got all those parts, we multiplied those numbers together to get the total change that we want to see in weight 5. Once we get the total change we want to see in weight 5, which is right here, we multiply that by our learning rate. This is how big of a step we want, because mind you, this is only a ratio. It doesn't tell you how specifically much, it just tells you its relation to all the other weights that we want adjusted. Then we went ahead and updated the value of weight 5, and this is the new value for weight 5. And in the same way, we could get all the other weights of the output layer weights. So these ones right here. Now, to get the weight changes that we want for all these weights, we have to go through first finding H1's contribution, and mind you, it goes for every node. So if there are more output nodes, then it would have to go through all those, and then you would just find its contribution to that. If there are more layers, then it would still propagate through all the different nodes. So if there's another hidden, let's say this was a hidden layer, then you would have to find its contribution to those, and then you would still have to find each one of their contributions to the output layers. So the more nodes and more layers you have, the more complex the computations will be. So anyways, the last thing we did was to find the contribution of weight 1 to the total error, which was first we had to find, if we're going backwards, the contribution of weight 1 to the output of H1. That's that guy right there. Then the contribution of the output of H1 to its activation. That's still right there. Then the contribution to the activation of H1 to both Y1, which is right there, and then the contribution of H1 to Y2, which is that one right there. And then you have then you multiply those numbers against we got all those values right here first. There's that one, there's that one, there's that one, and that one. Oops, there should be, where's it? 1. Oh yeah, 1, 2, and 3, and then it's right there that we calculated it. We multiplied all those numbers together to get that one. That's the change that we wanted in weight 1. And then, in the final step, we went ahead and updated the weight. So that's the change we wanted, times the learning rate, subtract it, now you have all the value. So that's all we have for this lesson. I hope you enjoyed the video. A lot of this one was unscripted, but it would have been more difficult to script all that while going through it. So if you had any confusion, I recommend that you definitely look over each one of those pages. Again, I'll be doing a show of each one of those pages individually, so you could just look at it and maybe write it all down and then go over the example while I'm speaking it through. But other than that, if you have any questions or you like this video, please like it, share it with everyone, and comment. I want to thank you for your time and enjoy the rest of your day. If you like this video, please hit that like button and hit that subscribe button. It helps this channel grow and make the content better. I'll be doing more projects along the way. And I'll do shoutouts to videos that I use for research and include the links. Any questions, please use that comment section below. Have a wonderful day and be your own successful. The 2 videos I want to give a shout out to that helped me with my AI research and inspired this video series were the first one by 3 Blue 1 Brown, What is a Neural Network? It's a great series, I recommend you all check it out. It's a great series for understanding the theory and what they are. And the second video by Naveen Kumar, Backpropagation and Neural Network. His video is a great one because it does a handwritten example, which I'll be doing in the 3rd video.